Jelena Klinovaja, if you meet somebody at a party, somebody who does not know you and asks you, oh, what are you doing? What are you telling them?
So usually I say that I do research in physics, and quite often you hear first reaction, oh, I was so bad at physics at school. And this is, one gets used to it, and then one tries to explain a little bit if people are interested in what exactly now research with.
You were bad in physics in school?
No, people with whom I talk usually tell me first reaction that they were very bad at school in physics.
Yeah. It's the most hated topic, I think, isn't it?
Yeah, I think it looks like we compete even with math. And
Why did you choose physics?
So for me, it was also not a while from the first sight. I was always interested in math, and math in elementary school was my favorite subject. When physics was introduced a little bit later in our curriculum, and at the first sight, I also was not super excited. But with time, I kind of grew to love it. And in our case, we also had the competitions at school in physics, math, and one gets involved in teams. And when you see it more and more, and you see how much more versatile could it be than just the standard curriculum which we had at lessons. And then one gets involved, one likes to work with people. It's also a very collaborative environment, and one gets slowly in more and more.
So this is the environment which attracts you. What is the topic that attracts you?
So the topic, I think, when you're at school, for example, is just starting physics, when you cover a broad range of topics. But when you go to university, when you start already to specialize, you listen to many different lectures, and then you choose what do you like, particle physics, or for example, condensed matter. This is my field. And in condensed matter, which is again a very large field, you can choose in which direction you want to go. So for me, it was always clear that I want to study more theoretical physics. So I never consider myself to be an experimentalist. And from theoretical physics, let's say, research in quantum physics was always one of which attracted me the most. So the challenges and...
You mentioned theoretical physics and experimental physics. Usually at the universities or in the schools, those lessons with booms and bangs, the experiments attract most people. And you've been attracted by theoretical physics.
Yes, I like that it was more structured, that you can derive things one from another, but it's very logical. There's no jumps in understanding. And this was what I found, let's say, from all subjects in natural science was the most appealing to me.
So what did you present in your talk here at the conference?
So in this conference, I presented first my area of research, giving first some short introduction about different computational approaches, comparing conventional and topological, because in my team, we work on both of them. We work on spin qubits, but we also work in the direction of Majorana and parafermions. And I tried to compare these two approaches to see and to kind of update where the status of a field currently.
But you work in theory.
Yes.
And there is a saying, the proof of the cake is the eating. So somebody has to prove with experiments what you calculated. Is that provable?
Yes,
in practice, what you are elaborating?
Let's say in our field, it's condensed matter, so it means that we work very closely with experimentalists. So the prediction which we do, or results of our work which we publish, are very clear idea to experimentalists. Okay, go to the lab and try to see it. And we have many successful collaborations also with several speakers which are at this conference, but we had works together which were motivated, let's say, by our theories. So we had our theory and afterwards we experiment, or it was even sometimes other way around, there's experiment and the explanation is not obvious, and when experimentalists approach us and then we develop theory for given experiments. So in our field there's very strong collaboration between theories and experimentalists.
So the one is not possible without...
Yes, I mean, of course, everyone would say that physics is an experimental field. Yeah. So we, of course, build up theories. But only what we can say sometimes for sure that something is not possible, right? If it breaks some fundamental laws, then we can say, okay, theoretically, do not try. It should not work out. And then we can maybe save some time of experiments. But the majority of cases, we give ideas. And of course, you can never be sure that all theory holds, because we always do approximation. We never can describe precisely, and when we need confirmation for an experiment to know that what we discussing or proposing is indeed true. And sometimes, of course, it's very difficult because constraint which we could put, let's say, on the quality of material, maybe it's something which we don't have now, maybe it would come only 10 years later.
Perhaps the prediction was correct, but the experiment was not good enough.
No, quite often, let's say, there's some predictions which are difficult to test because you cannot enter the parameter regime which is needed.
Sometimes it takes decades between the prediction and the experimental proof. I remember the Higgs boson was predicted in the 80s and proven 30 or more years later. So this could mean that something you calculate today will be proven after your retirement.
Yeah, very nice. But I think it's also, let's say, it's also interest, right? Because experiments which are done in physics are also expensive. And with limited resources, each experimental team decides in which directions they want to go, which one predictions the ones they test, and how realistic it is at a given moment. And quite often, of course, experiments are done and you discover something different, not what you were aiming at. And this is also totally fine.
This is totally science. But one could say it's perhaps serendipity, or I talked to Alex Müller and Bednarz, those who won the Nobel Prize for discovering new high temperatures, superconducting effects. And they said, well, we knew what we were looking for, but at the end it was kind of coincidence that this thing worked. Yeah. So how is it in your work? Has serendipity a place? Or
Okay, in theoretical physics it's maybe less because we kind of manipulate formulas, so we don't expect much surprise. But of course, sometimes it happens. So let's say you have sometimes idea what you want maybe to try with combination and to see what would work out. And quite often it's disappointing. If you find the fact, but it's so small that it's maybe difficult to measure. And then you drop such project, and sometimes you find the facts much stronger than you initially even thought it will be. And then, of course, it's kind of surprise.
Could it be that the effect is here, but they don't see it because the measurement is too little accurate?
Yes, this is always a problem because we can predict how large this effect should be, and they need to be in the right temperature regime. Let's say in the quantum mechanics, many calculations which you do are more in the approximation of temperature equals zero, and it means like our experimental colleagues are forced to cool down as much as they can, but there's fundamental limits, let's say, in a given crust at which temperatures one can achieve.
And we are talking about temperatures around 273 degrees below zero. This is really, really, really cold. This is what you mean. It needs a lot of energy to cool down the systems to that. So talking about that temperature, will quantum computing ever be applicable in a broad field, because it's so difficult to build these conditions where these effects happen, or will it always be something that is happening in the labs?
No, I assume you can make it commercial, because the cooling which would need, let's say, for many of these proposals one has are not, let's say, much worse than you need, let's say, when you go to MRI and you use superconductors, when they also need to be cooled down. So I don't think it would be a fundamental problem. The problem could be only like how much power we would need to cool it down and how much more efficient. So in general, there's a belief that quantum computer will be more energy efficient than classical computer for large-scale problems. And this is one of the gains.
But still, there is a gap between research in which enormous efforts are done, as we see here represented at this symposium, and the practical application. Could it be that the gap is too big? I refer to another phenomenon. This is the nuclear fusion. Since decades of years, they are predicting nuclear fusion is possible, but in practice, it's almost impossible because it's so hard to achieve these conditions. Could it be that quantum computing is too difficult to be applied in a wide range?
I think at the moment maybe it's difficult to say, but let's say quite often I think a similar example with nuclear fusion, when you have something which gives you huge gain, you would try until you see that it's indeed is not working. So again, at the moment, the promise is so big that we should continue trying it and to see. But at the moment, we do not see fundamental principle which would say, okay, it should not work out, or is it impossible? So all problems we currently face in the field, we still believe that we can overcome it. And it's kind of many experimentalists working in the direction how to overcome it. And we can see huge progress done last 10 years.
Which will be the fields where that benefit from quantum computing most?
I think first is modeling of any phenomena which include quantum mechanics. So it's chemistry, biology, when you need to model molecules, you need to try new drugs. But of course, there's also speed up in computational algorithms. Like, let's say when you solve a problem of factorization of numbers, it would be a problem, let's say, for bank and security. So there's many applications which could potentially be interesting. And as we heard already in this conference, there were many talks from companies who already tell how they going to apply these quantum algorithms for their everyday problems.
And if your neighbor asks you, will I profit from your work, Jelena? Imagine your neighbor, how do I profit from your work? How will it affect my life?
Well, I would say, let's say, fundamental science is not something that you would see it tomorrow in the supermarket. And quite often, let's say, if you look what was done in this field 30 years ago, I mean, all iPhones, everything is coming from this field, from research, but you cannot, 30 years ago, no one said, okay, you would have iPhone, right? But definitely you can say, let's say, if quantum computing would come, we would all profit from education, from optimization of various algorithms, how, let's say, infrastructure functions, how we optimize, how we use different types of resources, including energy. So this, I think, it would be maybe not personalized, but it would be for entire society. And of course, there's also like the field of quantum games, right, which we use now mostly for educational problems. So maybe it would be someone likes quantum
games.
Okay.
Describe me, what is a quantum game?
So quantum games is kind of, currently it's educational project. So there's many research problems, sometimes especially in quantum algorithms we are facing. And sometimes even solution is not known. And one of my colleagues, I think James Wooten, he had idea also with IBM to develop an app where you can play, and the result, the problem which you solved is connected to solutions we are searching also in our research project. But when you have an app, it of course optimized, it looks like a game. And I think there was many people who downloaded this app and they were playing with it. And just before a conference on Sunday, we had also collaboration from University of Chicago, that they have developed Quantum Casino. And it's again an outreach project for kind of high school students, also for adults, who can come and play games in which rules are determined by quantum mechanics.
So could one say this is then like you use the crowd to contribute to
yes,
research?
Yes. Sometimes you kind of assume that if you give some problems which we don't know how to solve it, but you can sometimes reformulate it in terms of games. For example, it's a combinatoric problem. When you can find out that people sometimes playing could find the better algorithms how to resolve it as scientists who work on it. Because it's again, you have math which helps out, and this is, I think, maybe also important for development of our society, that we involve everyone who is interested, and that you can do some small, be involved in science even without being a scientist by your profession. Because I know that many people genuinely interested in scientific progress and scientific research, and they read books, and also some of my neighbors sometimes indeed come with questions about physics because they heard and they're not sure. And I think it's our duty as a scientist also to give it back, and not to keep people away from science, not to protect it, say, okay, this is out, don't tell us. No, we want to have this communication.
I like this idea of involving people, ordinary people in science very much. And I will want to conclude our talk. I thank you very much.
Yeah, thank you.